All right, so we got two of these more circle problems that are due to 11 and 12. Like I say, we'll have a quiz on this stuff next week. So why don't we look at one of these? So 211, unless someone wants different, we could, but I got 211 kind of ready to go. 211. All right, so this is a process. It's kind of a long process, a little bit detailed, I know that, but I would encourage you to study it this way. There's a series of steps you go through. These types of problems aren't tricky, or they don't require you to figure out how to do them. You just have to apply the process. So I would encourage you to figure out the process. Okay. So this is Morse circle. Now, what Morse circle is a method that was developed a long time ago to do biaxial problems. It does the same stuff we've been doing with the equations. It's just a different method. It's a method from a different era when they didn't have all the electronics to solve things. So this is an older method that was used a long time ago, but it's still used today. All right, so here's the gig. Okay, so what you want to do is you want to start off. I just draw a big circle kind of in the middle of that grid on the paper, okay? Now, a circle doesn't have to be perfect, it's fine, but I just draw a circle. So that's step one, okay? And then what we want to do is identify the points on the circle. Now, normally I'd think to put in the axes and then put the circle on, but to me it works better to draw the circle first. Then I adjust where I put the axes. And the deal is with this is if I put the axes in first and the circle's way over to one side, now I got to draw this little circle. It's better to have a big circle and adjust the axes. It just works better, okay? So I draw a circle, and then what I want to do next is I want to identify the stresses on the two cardinal planes, the x and y planes, and those are called A and B in this method, okay? So what I want to do is, instead of calling them the x-plane and the y-plane, they call them points A and B. That's pretty common when you read books about Morse circle, that they do that. So, all right, so we just want to figure out what the stresses are on the x-plane. That's point A. So the 60 is positive. The shear then, we've gone over this a few times, but it's always worth it to remember this stuff. Okay, we're looking at this shear. Just by convention, that's the shear we look at. Okay, there's nothing magic about it. Someone just decided to do it that way whenever they developed all this stuff. You look at that one. If you hold a piece of paper on the desk and push on the right-hand edge, push it up, it'll go counterclockwise. So that's positive 60. Excuse me, I'm sorry, positive 15. Positive 15 for that. Okay. And then you look at the other plane, the y-plane, which the y-axis is normal to. We call that point B. And that's got a normal stress of 20 on it. And the shear will be equal and opposite to the one you got for A, so it's negative 18. Okay, and if you look at that, if you look at that drawing, and there's the shear, that would rotate that rectangle clockwise, is what it would do. So that's why it's minus. Okay, so we get 60, 15, and 20 minus 15. Now the y values, which represent the shears, should always be equal and opposite in sign. Always. Okay. All right. Now, those are points that are 90 degrees apart on the element, so they make up a diameter on the circle because the circle is based on the equations, and the equations are based on angles of 2 theta. Okay, that's why that happens. So points A and B make up a diameter of the circle. So if you can find the midpoint of AB, you have the center of the circle. So what you do, you take the x values for A and B, add them together, and divide by 2. In this case, it comes out to be 40. You can calculate the y-ordinate, but it doesn't matter. It's always 0, so you can always count on that being 0. So what I have now is a diameter that goes across the circle. It starts at A, 60, 15, and it ends at B, 20 minus 15. The center is at 40, 0. Now, once I've drawn that big circle, I know where A, B, and C are. What I'll do is I remember that shear is positive down. Okay, that's kind of unfortunate, but that's how it came out. By putting shear positive down, they preserve the direction of rotation. So for instance, if I want to get from the vertical plane to that plane right there, CD, I'm going counterclockwise. That is also the direction I'd use on the circle. That's why shear is down, so those two directions will match. Had they put shear, the y-axis going positive up, counterclockwise on the element would have been clockwise on the circle. So they figured it was less confusing just to have shear positive down, so that's how it's drawn, okay? Okay, what I noticed then is I've got point A is further right and it's in the below the x-axis. Point B is to the left and above the x-axis. So that allows me to draw A and B in their approximate proper locations on the circle that you put on your page, your big circle. And then you know C's in the middle. And then from that you should be able to get those axes in there. So that's kind of the steps I go through to get a drawing that makes sense. If y'all are with me there, okay? All right. So now I've got, that's step one, is get that diameter in there, get the center, and then you got your circle. All right, now the next thing to do is to make a triangle out of the diagonal line, which is a radius that goes from C to A. So it's kind of like applying the distance formula. I don't know, whenever you learn that in trig or something like that. Okay, so what we do, we make a right triangle out of that. We look at delta x and we look at delta y. Delta x goes from 60 or 40 to 60, so it's 20. Delta y goes from 0 up to 15, so that's 15. So what I've got there is a right triangle with sides of 20 and 15. So what I can do now is I can find what the hypotenuse is, which is the radius of the circle. It's the square root of the sum of the squares of the two sides. Then I can do an arctan of y over x and find the angle. I call it alpha. Most textbooks don't. I don't know what they call it, but I just call it alpha because I don't want to call it theta, because theta means something, you know, on with our sketching and all that. So I don't use theta. So I just used alpha, just to give it a name. Okay. So what I got now is a circle, and then I've got a right triangle put in there that goes from the midpoint of the circle to point A. And I've got that thing completely labeled. I got x, y, I got the hypotenuse length, which is the radius of the circle, and I got the angle there, okay? So that's all pertinent information, so it's right on there. Okay. We good with that? All right. Now the next thing to do is to use the circle to find some stuff, okay? And the stuff you want to find are the cardinal points of the circle, all right? So you want to figure out where these points are. If you use AutoCAD a lot, those are where the quadrant O-snaps are, but most of you probably don't use AutoCAD that much, but they're the cardinal points of the circle, 12 o'clock, 6 o'clock, 3 o'clock, 9 o'clock, whatever you want to call them, okay? You want to find those, all right? Now that's easy enough to do because you got the center and you got the radius. So you just take the center ordinate, 40, add the radius of 25, you get 65 on the right, subtract 25, you get 15 on the left, and then the shear, which is the y ordinate, is plus or minus 25, okay? So what you just found out is the maximum normal stress, the minimum normal stress, and the maximum in-plane shear stress, just by knowing the radius and the center point, okay? Now, as I mentioned, if you're in 1890, that's pretty good, you know. You just saved yourself a whole lot of work, and you just got the design values for designing whatever the heck it is you're working on, okay? Now, I overheard some of you talking about taking tests and all that and how you get pressed for time and all that. This is what I call low-hanging fruit, okay? Be able to at least do this, because you'll get a bunch of points, right? So just advice for taking tests and quizzes and all that. Just know at least how to do that. Find the center, find the radius, and do the pluses and minuses. You get the cardinal points of the circle. Those are the principal stresses. Okay, that's all pretty straightforward. So we good with all that?
What triangle have the first stress?
Okay, yeah, okay, I'm calling out not only the stresses, but the angles. See, what we have here is the circle is based on the formula. The formula, if you look at it, formula 25, formula 26, they have an angle of 2 theta in there.
Yeah.
And so you gotta, if you want reality, you have to take that angle from the circle and have it. That's what's happening in reality. Okay, so that's why I'm taking half the angle. So yeah, you're right, I forgot to mention that. I'm calling out where these are located, okay? So what I'm doing, I'm saying, okay, from A, the vertical plane, to the plane that has sigma 1 on it, I got to go counterclockwise 36.87 on the circle, so half of that is 18.4 in reality. Okay, so I didn't ask you to draw sketches, but if I had, you would have just gone 18.4, gotten yourself an element in there. On that plane, we got 65. On the plane making a 90-degree angle with that, we got 15. So that would have been, there's the principal stress sketch right there. Okay, no shears on that one, right? And then the maximum in-plane shear sketch, you got the 18.4, 45 more will get you 63.4, and then you got an element there. On that particular plane, which is the one up here, what we've got there, I think, is we got a negative shear stress, right? Yeah, we do. So on that plane, we got a negative shear stress. That would rotate the element clockwise. So those look like that. Now, I didn't ask you to do this, but I'm just illustrating what the heck's going on here. We got 25, and then we've got the average normal stress X on those planes, which might be significant if you're designing that, because not only do you have a shear of 25, you've also got some tension of 40 kind of stretching those planes apart. That might facilitate that shear and make it more apt to happen. Yeah.
Is it always the case that at the maximum shear, the average normal stresses are?
Yep. Yeah, that's every time. It's always that way. Yeah. So on the maximum shear planes, you've got the average normal stress, at least for the in-plane, of course, just the in-plane stuff. Yeah. Okay. All right. So that's what's going on. So remember, what this is a calculating model, okay? It's not a model of the element or anything. It's just a calculation device, a very simple graphical calculation device that somebody came up with 150 years ago. It's kind of like Stonehenge or something, okay? That's kind of what it is. It's just a simple thing that some really smart person who didn't have all the electronics came up with, is what it is, okay? It's just a device for calculating, okay? All right. Okay, now to get into the rest of the stuff with the angles and all that, let's just say we want to find the stress on that plane right there on CD and also on DE. We can do that off the circle, just like you can do it with the equations, okay? You got to do a little bit with the angles, though. All right, so the first thing you do is you rotate an angle equal to twice that 35-degree angle. So you're going to go twice 35 is 70. You're going to start at the point on the circle that represents the vertical reference plane that I showed there. You're going to rotate counterclockwise twice 35. So you're going to go 70 from there. So you're going to do this, 70 degrees. Okay? And then you're going to just draw a line up here and see where it intersects your circle. And the coordinate of that point will get you the stress on plane CD. And if you remember our first run through this, we didn't do any trig. We just plotted it up on graph paper and counted squares, right? We got a pretty good answer. But unfortunately, nowadays, we do it in a more analytic way with a calculator. Okay. So the way we do it analytically is we take another triangle. See, that's how you work with the angles on this stuff. You work with triangles. So we got a right triangle in there. And we want a right triangle, so we have a hypotenuse, an angle, and then an x and a y side. The x and the y sides will help us to find the normal stress and the shear. Okay? So the hypotenuse of the triangle is the radius of the circle, 25. And then the angle is, on this particular one, we're going counterclockwise 70, but we know we're already 36.87 below the horizontal. So if we take that 70 and take away 36.87, we get 33.13. That's the vertex angle of that triangle. So what we know is it's got a hypotenuse of 25 and a vertex angle of 33.13. So we can do the trig there on the angle on the hypotenuse, which is the radius, okay? And we can come up with the two sides, 20.9 and 13.7. Okay. Now we know the sides of the triangle, so if we want to find the x value of that coordinate, we got to remember to add that little offset, because the center of this thing's not at 0, it's at 40. We got to take 40 plus 20.9 and get 60.9. And then we got 13.7 up above the x-axis. Well, that's negative shear, so that's negative 13.7. All right. And then what we can do is come back the other way. All right. If we want to know the stress on that other plane, DE's 90 degrees from CD, so we just double the 90 and get 180. We just shoot that line back, and we find the coordinate of that point. Same triangle, just rotated around 180 degrees. So 40 minus 20.9 is 19.1, and the shear is positive instead of negative. All right. So if we're looking at what's going on here on CD, what do we got? We got 60.9, and then the shear on that plane is negative. So it goes like that. So that'll go like that and like that. So what's the shear? 13.7. So the shears always meet in the corners. And then the normal stress on the other side is 19.1, like that. Okay. So again, I didn't ask you to do that, but if I had, that's how you draw that sketch. That's what's going on. We got any questions on that one? All right, so that's how this stuff's done with Moore's circle, okay? And this is just, the steps I went through are the steps you use when you do it. So draw a big circle, figure out where A, B, and C are. Put your axes in. Remember, shear is positive down. Do the trig on the radius that goes from C to A. Make a right triangle out of that and do the trig. Okay. Find the length of the line and the angle. Take the center and add and subtract the radius. Do that for the y ordinate also, and you'll get the principal normal stresses and the shear stress, maximum shear stress in plane. And then if you have some other element you want to figure out, look at its angle, double the angle. Remember to do that. Start at a reference point on your circle and rotate in the same direction as that angle. Figure out the coordinate of the point that you land on. Find a right triangle. You can use the radius as the hypotenuse, and hopefully you should be able to get a vertex angle that you can work with. Okay.
Where does the 125?
Oh, 125. What I've got, see so the question is, where does this come from? It comes from knowing this and adding 90 to it. Because what's up? I'm saying what's the stress on plane CD? I gave you the 35 for CD. And then if the DE makes a 90-degree angle with that plane, so you take 35 plus 90 more and get the 125.
Right, but we took the 35 off of our A, so wouldn't it be another 90 degrees off of that? It would be 90 degrees plus our 33.13.
Well, okay. So let's see. So let's just kind of. So what I found here is that theta CD is 35. So on the circle, I got to double that. So it's 70 degrees counterclockwise. And I'm gonna, when people ask questions, I just run through and just do the whole deal from A. Okay, A is the point on the circle that represents the vertical plane on the element. So theta DE is 35 plus 90 more. It's 125. So on the circle, it is twice 125. It's 250 counterclockwise from A. It's 180 more than the 70.
Just saying
On the element, yeah, not on the circle, yeah. And I understand your question, though, why you're asking it. But the thing to remember is that circle is a calculating device. That's what it is, you know. That's all it is. Okay. All right. We're good with that. So what's going on there? I'm going at 180 more than 70. That's on the circle. So I just shoot the line back is what I do to accomplish that. Same triangle, just rotated 180 degrees. Other questions on that? Yeah. All right, for those of you online, I just handed out a test review. And let's see. So that's under the test review downloads. I think you can go there and get it. There's a couple parts to it. There's a list of stuff to be looking at, and then there's also some old test problems. So, you know, if you haven't had any of my classes, this is usually what I do for tests. I just give you a list and then just some old problems, you know. Now, don't read too much into the review problems. You know, that's just some stuff that's on my computer and I pulled them off. Okay, so just look them over. They'll get you some example of what the test might look like, but I'm not trying to say if you just do those problems, you're ready for the test. It's not that way, okay? They're just examples, that's all. So don't read too much into them. All right, so what do we got here? We have got simple stress and strain, sigma and tau. And then epsilon and gamma. I'm reading at the top up there. All right, so that's so just be sure you know page 120. Okay, it was that's just that stuff with the Greek letters on it and the names. So just be sure that you know which variable to use at the right time. Okay, that's kind of an issue in this class. So know what tau means. Know if I ask you find the shear stress, you should look on the formula sheet for tau, you know, to connect those dots, okay? I think that's page 120. The other thing we did there was I think it was page 200, and I can't remember these pages, but we just did a simple example there to show the difference between normal stress and shear. It was a block that we kind of went through, and I'm pretty sure that was page 200. But I'm not 100%. Yeah, 200, okay? All right, and then we did the deal of finding the internal forces and stresses when multiple forces are applied. That was some of the first homework we had, where you make a cut inside, you know, so find the reaction. And then cut through the area you want to find. And then use sum of f equals 0 for one entire side or the other entire side. You with me on that? Don't just pull a little chunk out of the middle. You got to take one entire side or the other entire side. That's what you got to do. Okay. Okay, stress strain diagram. Looks like that, right? Straight up, yield, strain, get that Harding phenomenon, then failure, right? Something like that. So stress and strain. Know the areas of the graph and how to calculate things like yield stress and that sort of thing, okay? So that was a homework problem. 111, I think. 111, okay. All right. Modulus of rigidity, that's actually the shear modulus is the more common name for that. It's G. Poisson's ratio is new. That's that ratio between lateral strain and axial strain. Axial deformation, we have that formula, delta is PL over AE. You could do that with multiple forces, break the object up into pieces. Okay. Statically indeterminate problems, the first thing you want to do is recognize them, okay? And that seems to be a problem on these midterms is people don't recognize them. So understand that. Can you solve it with statics? If you can't, you got to use strengths. It's a two-part process, right? What you do, so step one is to recognize them. Step two is to use statics and delta equals PL over AE, right? Okay. Temperature-induced stress and strain, axial loading, okay. Normal and shear stress, we just have the formulas for doing that. Just remember to use the proper reference angle, proper sign on your force. Biaxial loading, state of stress at a given angle, principal and normal stresses, and maximum shear stresses, Morse circle. Now Morse circle, what I'm going to do, I'm going to pull that out, so that won't be on the midterm. That'll be on a quiz only, okay? So you don't have to worry about that for the midterm. We'll just have a separate quiz on that later next week, okay? So as far as studying goes, okay. Also, you should be able to draw sketches and show what things look like if they break in different modes. Okay. Okay, we got some vocabulary there: stress and strain, normal stress, tension, and compression. Normal stress is also commonly called axial stress. Right? They're the same thing. Two words for the same thing. And then shear stress. And then there's all these words that start with the letter D: deflection, deformation, displacement, and delta. Okay, they all mean pretty much the same thing. How much something changes length or changes position. So it seems like, I might use different words. They seem to have this different way of fitting into sentences better in some ways than another. I'm not quite sure. English has about twice as much vocabulary as most languages do. We got all these little shades of meaning on words. I'm not quite sure why, but anyway, they all begin with D. That's the easy way to remember that. Okay, they all mean the same thing. Okay. So we good with that? Okay, that's the list. So we've gone through all the stuff now. All right. I just got some examples. On that one, I just asked you, I showed you a normal stress strain curve, and I asked you to find E. Okay? We can go over these on Friday if you want, if you have questions on them. The next one there, find the deflection of point C after the loads are applied. That hatching means a reference point that doesn't move, so that's the reference point there at A. It's not moving. That's the meaning of the hatching. This next one, we got a bar. It's in between the two supports, and the temperature goes up. It's going to try and get longer. The supports will not allow that, so stresses will build up in the bar. I want to know the normal stress and the shear stress. So that's an axially loaded bar, uniaxial loading. Okay. Looks like a little bit of a problem there to figure out the deformation. How far will point A move to the right? Okay, I'll let you kind of look at that, but think about what type of stress that is and that sort of stuff on that one, okay? And how and what the different definitions are when you're going through stuff with that. Okay, 3 supports welded to the floor into a lightweight tank. No stress in the supports. Then we pour in 180,000. This is on the back side. This is page 2 if you're online. 180,000 newtons of water is then poured into the tank. Find the force in that central post there, CD, and the deformation of CD after the water is poured in. Okay. So that one, you're going to have to use a little bit of strengths on that one to get that one figured out. Okay. Okay, got a Morse circle one. That'll be on the quiz, something like that. Okay. So that's one you could practice on. All right, then we've got find the normal stress on this plane. If this normal stress were to cause the plate to fail, make a sketch that shows the appearance of the plate after failure. All right, so to find the normal stress on that plane, you just plug 48 degrees into the formula. That's really about all there is to it. So you got to identify sigma x, sigma y, tau xy, and then the angle to the plane from the vertical reference plane. So that's 48 degrees you want on that one. And then you just plug the stuff in. I mean, that's really about it. And then if that fails in tension, it'll just split and split apart there. Okay. So that's just some old problems off a test. Why don't we touch on one or two other little things here that seem to come up. And we can go over this on Friday if you've got questions. Cool. Why don't we start with what we were just looking at, that Morse circle example there, or the problem 211. Why don't we just look at that for just a second? I can find the dang thing. Nope, that's not it. Oh, I closed it, didn't I? Yeah, I think I did. This is it, maybe not. Yeah, I know. There we go. Okay, now you got to fill in the answers on this thing. Down at the bottom, if you look at page 211, okay. So if you took notes on this, see if you get those answers filled in properly. Down for the problem 211. So you got a bunch of answer blanks to fill in. Let's see if we can get those figured out. So the normal and shear stress on CD, the normal and shear stress on DE, the maximum tensile stress, the minimum tensile stress. I don't know what I'll ask you. The maximum in-plane shear stress, I'm going to ask you. Got a lot of stuff to answer on that. It's on page 12A. So why don't you look at what we just did and fill in that table. It'll take about 5 minutes. So down at the bottom of page 12A, have a look at what we did. And hopefully you got some decent notes on that, and see if you can fill in that table. Okay, I'll pause the recording for those of you online. So why don't you pause the recording here and then do it, and then start it up again, and we'll go over it. Okay, how about the normal stress on CD and the normal and shear stress on CD? What are they? What's the normal stress on CD? Okay, what's the angle for CD? 35. So there's the normal stress on CD. Okay. And then here's the shear. Okay, and see, you got to connect the fact that angle CD makes a 35-degree angle with the vertical. Okay. And then for DE, you're 90 degrees more, so you're at 125. So here's the normal and shear stress at DE. Okay. So we got 60.9, negative 13.7, 19.1, and 13.7, okay? All right. Now, what's the maximum normal stress in plane? What's that? The maximum axial or normal stress. Where is that on the circle? Okay. about as far right as you can go, okay? That's the extreme point on the circle. That's where the normal stress, which is represented by X, is maximum. Okay? So you're going to take the center point and you're going to add the radius to get that. So 40 plus 25 is 65. Okay? That's over here. The minimum normal stress is over on this away. It's as far left as you can go in the circle. 40 minus 25, it's 15. The maximum shear is at the top and the bottom, plus or minus 25. The average normal stress is the X value in the middle. Okay? So 65, 15, plus or minus 25, and 40. And then the angles are based on half of the angle that you get off the circle. So to get to the 65, you start at A over here. You come this away 36.87 when we trigged out that triangle. Half of that's 18.4. Now, once you've got 18.4, you don't need to measure the rest of them off the circle because you know the other principal stress will be 90 degrees more, okay? So 18.4 plus 90, that gets you 108.4. And you know the shear will be 45 more. Okay? So once you got one of them, you can get the others. All right? So we're doing all right with that? Okay. So, we just want to be sure that, you're comfortable filling in these tables, that you can kind of connect the words here to what you're doing with the circle. All right. All right, now the other thing we want to look at here is just that little review that we did, because there's another little thing that comes up sometimes, and I just want to be sure that, or do what we can do here to get these ideas across, and that is this biaxial review stuff, because we do two different things with biaxial stress, and they're different, okay? And I want to be sure, trying to ensure that everybody understands the difference. The first thing we do is the simpler of the two. We just say, okay, what's the stress at this angle? Okay? And in that review we did, it was this problem here. Find the stress at 25 degrees. So this is simple, and you want to keep it simple. If the question is to find the normal and shear stress at on this plane, and you know the angle of that plane, you just take that angle and you pop it into the equations twice. First, you pop it into the normal stress equation, 25, and then you take it, and after that, you put it into the normal shear stress equation, 26, okay? Because all we're asking there is what's the stress at that angle. So it's not complicated, and you want to keep it simple. So for this example, we used 25 degrees and we plugged it into equation 25, and then we plugged it into equation 26, because all we wanted to know is the stress on plane AB. Okay. Now the next example gets a little bit more involved. The next example, we were trying to figure out what are the maximum stresses on this ceramic plate. Okay. Now on this one, you got to find the angle first. You got to use that tangent 2 theta formula and find the angle at which the maximum stresses act. Okay. So this has one more step than the previous one. On the previous one, you're given the angle. On this one, you're not. So you got to find the angle first with the tangent 2 theta formula. Then once you have the angle, you can plug it in to the equation 25 and find the normal stress. Okay? And there's two of them, and they're 90 degrees apart. Okay? Now the other thing with this type of problem, and we didn't do it in this example, but if we needed to find tau max in plane, Okay. We didn't have to on this one, but if the question had been to find tau max, and if we knew that theta 1 was, whatever the heck it was 11.6 degrees, what angle would we use to find theta tau max? 11.6 plus 45, right? And then we would have gotten what, 56.6 degrees, and then we would plug that into equation 26, right? You all good with that? Now, that's what you do when you're finding the maximum shear. That is not what you do if you just want to find the shear on plane AB. If you want to find the shear on AB, you just take 25 degrees and plug it into the shear formula. That's all there is to it. The only time you start adding 45 and doing all that is when you're looking for maximum values, because they occur on different planes. But if the question is just to find the stress on AB, it's just 25 degrees. Don't make it harder than it needs to be. Okay. All right. All right, so that's just a couple of things that have come up in the past. I just want to reiterate those points. All right, so we'll start in on some new stuff. It won't be on the test, but we'll start in on new stuff tomorrow, and we'll review this stuff on Friday if you like. The test is on Monday.